Hi, I'm Jonathan Aldrich, and today we're going to talk about static semantics and typing rules. The semantic analyzer in a compiler has two different roles. The first is to enforce static semantic rules. For example, we want to make sure that names can only be used in the scope of their declaration. Variables must be initialized before being used, and all operations must be passed data of the correct type, the type that they can use. The semantic analyzer also will annotate the program with information that's needed by the code generator and interpreter. For example, this might include clarifications. Does the variable x refer to a local declaration or a global declaration? The compiler needs to know that because it's going to generate different code for accessing the local declaration versus the global one. As we learned in Chapter 3, those variables would be stored in the stack for local declarations or in the static program space for a global declaration. Also, when we come to an addition, we need to know whether to compile it as an integer operation or a floating point operation. So we need to know the type of various operations and operands. Finally, we need to annotate the program with information about dynamic checks that are required. For example, does this array access need to be checked for an out-of-bounds error? Or perhaps a multiplication should be checked for integer overflow. One kind of semantic analysis is type checking. Type checking has a number of benefits. It finds program errors at compile time. For example, if you try to add true and 5, there's no mathematically defined answer to that question. So if we didn't type check at compile time, this program would result in an error at runtime. It's better to find that error early. Moreover, checking for these errors at runtime will slow the program down. If we do the check at compile time, we can avoid those runtime checks. Type checking also ensures that types are correct. This is helpful because types are important documentation for programmers. You'd like to know that the type annotation for an argument of a function really reflects what that function expects so that you can pass in the right kind of data to it. Finally, as mentioned in the previous slide, types help generate code. 3 plus 2 should generate different assembly code than 3.14 plus 2.5. We'll use either an integer addition operation or a floating point addition, respectively. So how does type checking work? Well, a type checker traverses the program's abstract syntax tree and computes the type of each subexpression. We'll use tau, the Greek letter, to denote types in the formalism that we present today. Our calculator language has two types, so tau can either be an int or a real number. The type checker relies on a typing context that maps every variable to its type. That's similar to the environment in an interpreter that maps variables to values, except when we're type checking, we don't know the values yet, and so we just keep track of the types of the various variables. We can formalize a type checking judgment similar to the one we formalized for dynamic semantics. Our type checking judgment states that in context gamma, that's the Greek letter gamma, that's the map from variables to types, or the typing context. So we say in type context gamma, expression E has type tau. Let's look at some expression typing rules. The first rule, tint, is an axiom that just shows that any integer literal n will have type int. Similarly, a real literal will have type real. When we come to a variable, we need to look up the type of the variable in the type context. So we look up gamma of x to find out what the type of x is in gamma. That will return some type tau, and that will be what we conclude is the type of the variable. For binary operations, we have two premises. We first type the left-hand side of the binary operation, E1, and get some type tau. We then type check the second binary operator, E2, and get the same type tau. So binary operands can either operate on integers or reals, but they both have to be integers or they both have to be reals. And so we express that by having the same tau in both premises. And so we have to substitute tau with either int or real, depending on what the types of the E1 and E2 subexpressions are. The float operation converts ints to reals, and we can see that in the type. The conclusion says that float of E is of type real, and it requires that the expression E have type int. Trunc is exactly the opposite. It takes an expression E of type real and gives us a truncated version of that expression that has type int by dropping off the floating point part. Let's apply these rules to a type checking example. Here, we are evaluating the expression 2.718 plus float of 1. 2.718 is a real, so we use tReal for that. 1 is an int, so we use tInt for that. We convert the int to a real using tFloat, and then we combine the part that typed 2.7118 and the part that typed float of 1 to conclude that the entire expression has type real. Now this is an example of successful type checking, but type checking can also fail. For example, if we leave out the float conversion, the expression 2.718 plus 1 will fail to type check. How does this actually work out? Well, essentially we try to start constructing a typing derivation, and generally for expressions we'll kind of work bottom up. So we can succeed in type checking 2.718 at type real and 1 at type int. But when we try to apply the natural next thing, the binop operator, which will allow us to type check the plus expression, right? Our circle plus, once again, can be any kind of binary operator, including plus. We'll come to a problem, right? Because E1 will be 2.718, and so tau has to be real in the first premise. But in the second premise, E1 is 1, and tau will be int. Now the problem is those premises work independently, but when we try to put them together, we need tau to be replaced with one thing, either real or int. And in this case, the sub-typing derivations require it to be real in one case and int in the other. And so there's a clash. The rule cannot be applied. So we call this a type clash, and a type checker would report an error. Our formalism doesn't show the error reporting, but when we look at implementing type checkers, we'll show how to do that. So our calculator language requires surrounding the 1 with the floating point conversion. Of course, real languages like C, might actually just convert the int to a real implicitly. That can be expressed with typing rules too. They just end up being a little bit more complicated to deal with the extra cases. Note that there's an interesting correspondence between the typing rules that we've given and the evaluation rules that we looked at in the last section of the text. So let's go back to evaluation rule for binops and compare it to the rule for typing binary operations. In both cases, we're evaluating or type checking some expression E1 opt E2 for some operation. In both cases, we do that by either type checking or evaluating the parts of the expression first, E1 and then E2. What's interesting is tBinop implicitly requires the two expressions to have the same type, and that matches the dynamic check in our evBinop rule. Our evBinop rule says whatever value we get from evaluating E1, call it V1, has to have the same type as V2, which is the value we get from evaluating E2. And so these line up, right? If we successfully type check this program, so with tBinop, then we know, assuming that the sub-expressions type check as well, we know that they'll give us, two ints or two real numbers. And so that check in evBinop at runtime will always succeed. What that means in practice actually is that a smart compiler that does type checking can actually omit the check from the evBinop rule. We don't have to implement all the checks if we know that we've already done them statically at compile time. And so that's good for the programmer because the programmer knows there won't be a runtime error where there's a type mismatch on this operation, but it's also good for the compiler or maybe for the user because the program will run fast. We can eliminate these checks. You can see there's a similar correspondence between the trunc typing rule and the evaluation for trunc. Once again, the typing rule for trunc requires that E have a real type, and EVTrunc requires that E evaluates to some R, and implicitly R is a real value. So once again, it's checking the type at runtime in EVTrunc, and that corresponds to the static check we're doing in the type checker. So this correspondence is not a coincidence, right? We designed these rules so they match up together, and it comes from a soundness property that we'll talk about later in this chapter. We can type check statements too. And in fact, that's where we get information about variables in our types. So remember that our statements are formalized as a linked list, and so just to be complete in our formalism, we have a T empty rule for type checking the empty program. It doesn't do anything. Every empty program type checks. When we have a type declaration, then we'll just add x colon tau to the context for whatever type tau x was declared to be, and then we'll go ahead and check the rest of the statements. So that's tdecl. For tassign, we're type checking an assignment x gets e followed by a set of statements. We're going to check e in the gamma that we have for the statement. That's the first premise of the rule. The second premise of the rule is going to make sure that x has the type tau that matches the expression we just type checked. And then finally, we type check the rest of the statements. Tassign is not allowed to change the type of x, and so we can use the same gamma throughout the entire rules. I've also written read and write expressions. Here read checks that x has some valid type. We assume read knows how to print both integers and floating point numbers, but we would like the sub-expression to be well typed. What this is really checking is just that x exists in the context. And so this is making sure that it's really doing what we call binding analysis. It's checking that x is bound in gamma. For writing, we similarly check that the sub-expression e is well typed. That means if there's any errors in computing e that are due to type errors, we'll detect them at type checking time. Otherwise, we just go on and check the rest of the statements that come after the write. Let's look at an example of how statements can type check. Here we're looking at a sequence of statements, int x, followed by x gets x plus 1, followed by the empty statement at the end of the program. Again, the empty statement is an artifact of the way we're representing this. Remember, we're type checking abstract syntax trees, and so we've already converted the input form of the program into an AST where the statements are arranged in a linked list, and we end with the empty statement. We're going to type check in the empty context, so I'm not putting anything to the left of the term style. Our first rule is tdecl, and that applies because our first statement is a declaration. The tdecl rule says we add x colon int to the context, which was empty before, and so our context now just has the mapping x colon int in it. We then type check the rest of the program. It starts with an assignment, and so we'll use tassign next. The assignment statement looks at the right-hand side of the assignment and type checks it. Here it's an addition statement, so we use the tBinop rule, and then we go and look at type checking x. We type check x by looking it up in the context x colon int. So here's the context x colon int. We look up x, and of course we get int, not surprising. So x has type int. Similarly, we use tint to find that 1 has type int, and so this whole expression has type int. Because we're assigning this to x, we check that x has type int in the environment as well, and then we type check the empty statement using the tempty rule. That completes the type checking of this program. Let's check our understanding.